Okay, we're going to split section 7.1 into two parts. This is chapters on scheduling. So where we'll pick up in the second part is on maximal paths. Okay, first thing, pretty much most of 7.1 is just looking at some vocabulary, so there's going to be a lot of me just reading things and explaining them to you. So first of all, a task. A project is made up of two or more smaller activities, and those activities are called tasks. And tasks cannot be broken down into smaller jobs, and one machine or one person, which you'll learn a little later on, which is called a processor, is in charge of doing that task. And the amount of time that it takes to complete a project depends on how many people or machines are available to do the work, and also how you assign these tasks to be done. So let's say that you're cleaning your house. If you're cleaning your house all by yourself, it's going to take longer than if you have a crew of people helping you. And you're able to assign someone to scrub the bathtub while you vacuum. Because obviously you can't do both of those at the same time if you're cleaning the house by yourself. So the house will get cleaner faster. So again, people or machines that are doing tasks, they're called processors, and the amount of time that it takes to complete the task is called a completion time. Now there are some things that you have to do in certain orders. So, like at my house, my dishwasher doesn't work that great, so I have to pre-rinse the dishes before I can put them in the dishwasher. And I have to put the dishes in the dishwasher before I can turn the dishwasher on to wash the dishes. So that's a precedence relationship. Pre-wash the dishes has to precede putting the dishes in the dishwasher. Putting the dishes in the dishwasher has to precede actually washing the dishes in the dishwasher. So they have a precedence relationship, also known as an order requirement. They have to be done in that order. Well, you have some tasks that are called independent because they don't depend on anything else. It doesn't matter when they're done in relationship to anything else. If we are cleaning up the kitchen, it doesn't matter when we put the toaster up. If we put the toaster up at the beginning of cleaning the kitchen or at the end, it just doesn't have any relationship with anything else in cleaning the kitchen. So here's another precedence relationship or preference relationship or order requirement. There are, several different ways to express this preference relationship. So here we're putting on socks and putting on shoes. So we have our regular looking graph, but you notice there's something new. There's an arrow. This says that socks have to come before putting on shoes. This becomes a one-way street. Have to put on socks, then you can put on shoes. So here these are independent tasks. It doesn't matter which order these are done in. They don't have any bearing on each other. So putting on a hat and putting on the coat, it doesn't matter which order you do those in, so you don't have an arrow connecting these. So we're looking for the group that has no preference relationship. If we bake the pizza, grate some cheese, and make the pizza sauce, well, that definitely has a preference relationship because we have to make the pizza sauce before we can bake the pizza. Fold some clothes, wash some clothes, hang some clothes on the line to dry. Well, they have to be washed before you can hang them out to dry. Bake a cake, toss the greens, set the table. I don't really see anything that has to be done before another task. So I'm saying that doesn't have any preference relationships. Frost the cake, bake the cake, set the table. Well, you have to bake the cake before you can frost it. So we have a digraph, which is short for directed graph. We looked at a digraph earlier. It was a regular graph except it had arrows in it. So digraph, directed graph, you have these one-way streets. You have to follow the arrows. So the points are still called vertices or a vertex, and the arrows, instead of being called edges, they're called arcs. I'll probably still wind up calling them edges, but their technical name is an arc. So use the digraph to represent the precedence relationship for a man getting dressed for a run in the summer. So a shirt, shoes, shorts, and socks. And we can set up a preference relationship, which is right here. Putting on shorts before your shoes. Put on the socks before the shoes, but there's not an order requirement here between shorts and socks, and there's not putting on the shirt. It doesn't matter where you put on the shirt. So let me back up one slide. So you have a digraph that has at least one preference relationship, precedence relationship, or order requirement, and you have what is called an order requirement digraph. And those independent vertices that we were looking at earlier are called isolated as well. So put on a shirt is independent and it's called isolated. So before we learned that a path has to be two or more vertices and they have to be connected. So we have a path that has two or more vertices on a directed graph is called a directed path. But again, we just call that a plain old path. So if we identify all the paths in the order requirement digraph represented in this replacing the old brake shoes, we could have T1, T2, T4, that's a path. T1, T3, T4, that's a path. T1, T2, or T1, T3, or T2, T4, or T1, T4. So you have lots of different paths as long as you have two vertices and they follow that precedence relationship, preference relationship, order requirement, whatever you want to call it, you have a path. So a path that you cannot extend it by adding anything to the beginning or anything to the end is called a maximal path. So in the previous example, T1, T2, T4, and T1, T3, T4 were maximal paths. We didn't have anything that came before T1, and we didn't have anything that came after T4. So that was a maximal path. So vertices that you don't have anything that can come before them are called sources. Sources are the beginning of a graph. You don't have anything that's feeding into a source. Now a sink is at the end of the graph. You don't have anything that is coming out of a sink. Now an important thing is that an isolated vertex is both a source and a sink, because it doesn't have anything feeding into it, it doesn't have anything leading out of it. So a maximal path starts at a source and ends at a sink. So back to our graph that we looked at before, T1 is a source because we don't have anything that's leading into T1, and T4 is a sink because we don't have anything leading out of T4. So we need to identify all the sources and all the sinks. Well, my sources, put on socks as a source because there's nothing leading into it, put on a sweatshirt as a source, and putting on a hat as a source because there's nothing leading into it. So we have three sources, so that definitely gets rid of A. Putting on a hat, that is a source. Put on a coat, that is not a source. So we know B is not it. C only has one source. D, put on socks, put on sweatshirt, put on hat. That's your sources. So since we've eliminated everything else, our sinks must be to put on a hat, which is a sink, put on a coat, which is a sink, and strap on snowboard, which is a sink. Now we'll pick up on maximal paths in the second half of 7.1.